Hey everybody. Well, as I promised, I'm going to come live from the lab today, or going to stream from the lab. We're going to be talking a little bit about instrumentation and some experiments in which we use chromatography. Before we get into that, just a few announcements. The final homeworks will be due on Friday, April 24th. Exam 3 is on Friday, April 24th. It'll be from 1 till 2 p.m. Now, the final exam will be on Friday, May 1st, and the topics that I discussed today will be on final exam, not this third exam coming up. So today, our lecture is going to focus on comparing gas chromatography versus liquid chromatography. Now, when we decide on what type of separation we're going to do, it really depends upon a few factors. First of all, it depends upon the nature of the sample. Is it a volatile, thermally stable compound that's in a liquid phase, or is it in a gas phase? Well, in that case, we're going to choose gas chromatography. Gas chromatography is cheaper, has less waste, and it can be done pretty quick. Liquid chromatography is useful for non-volatile solute that we can't get into the gas phase. It takes a longer amount of time. It's more expensive, and it does generate more waste in GC. So before we discuss whether we want to conduct an experiment involving liquid chromatography or gas chromatography, we're going to briefly discuss our modes of chromatography. The two modes that we generally discuss in terms of determining what type of chromatography we're going to conduct is either being considered normal phase or reverse phase. Now, the term normal phase, what that implies is that our stationary phase is polar. Now, for liquid chromatography, we're going to discuss that the mobile phase is important of having opposite of that. In normal phase, the polar stationary phase is going to have a non-polar mobile phase. And we'll be discussing that in more detail in a few minutes. Reverse phase chromatography is the situation in which we have a non-polar stationary phase. And for liquid chromatography, we're going to have a mobile phase that's polar. Now, the reason why we use reverse and normal, that terminology, normal phase just was introduced earlier. It was introduced first. We showed thin layer chromatography used silica plates that had selenol groups, and those were a polar stationary phase. And that was the first type of chromatography that we conducted. Later, we changed it. We found that it's more amenable to liquid chromatography to use a non-polar stationary phase. So we'll be discussing more about that when we get into our liquid chromatography section in a few minutes. Now, when we consider gas chromatography, the reason why we call it gas chromatography is because our mobile phase is going to be a gas. Normally, we call this our carrier gas. Typically, these gases would be anything from helium, argon, to nitrogen. We usually choose a gas that's rather inert. It's not reactive. Some people use hydrogen gas. The only problem with hydrogen gas in some applications is that it's explosive above 4%. Not good. So the stationary phase is within a column, and it's going to be either a solid or a solid support with a liquid surface on it. Now, the sample that we use, as we said, is going to be a gas, or it's going to be a volatile, thermally stable liquid. So the instrument, I have a block diagram of the instrument on today's PowerPoint slide. So I'm going to try to bring you up to base on what we use in an experiment. So this is the GC that we have in the laboratory. Move this up here a little bit. There we go. Everybody see that? Now let's look at what we have here. Now over here in the corner, I'm showing everybody, that's our carrier gas. And our carrier gas for this particular instrument, we're using helium. Helium is an inert, non-reactive gas, really useful for this type of analysis. Okay, this is the instrument itself right here. It's housed in here. Now, the sample that we're going to be introducing is going to be typically in the form of a liquid. And the liquid that we introduce is normally going to be from a syringe, just like this, a glass syringe that we would carefully aspirate or suck in some of our liquid sample. And remember, the sample is going to be volatile and it's thermally stable. Thermally stable because we're going to be changing the temperature a lot during a GC experiment. So we take our sample, we would inject it, and I'll show you where the injection is. Up here is where we conduct our injections. There's a little injection port. It has a little septum in there, and it has a metal plate that when we push down the injector, it signals to our instrument that the analysis has begun. So that's really important for when we conduct our experiments, knowing when we're getting our experiment to be initiated. Okay, now for the separation process. Key to any type of chromatography experiment is going to be a column. We need some type of column to have our stationary phase. Now, for GC, there are basically two types of columns that are used. One is a packed column, and one is an open tubular capillary column. So the first type we're going to just discuss is a packed column. Packed columns are typically composed of particles that are solid, and they may have a liquid coating on them. The columns themselves have lengths from about 2 to 6 meters, and they have an inner diameter of about 2 to 4 millimeters. Now, the advantage of using a column, this packed column, is that we can afford a larger sample amount. So that's really important for when we want to conduct an industrial preparative analysis where we're using large amounts of sample. Now, for working in a research lab, or if you were working in lab for this particular experiment, we're going to use an open tubular capillary column. So the columns themselves, whether they be packed column or the type of column that I'm discussing now is a capillary column, these are inside an oven. So I'm going to open the oven up. Here's our oven. There's our oven, and in that oven is where our capillary column is housed. Now the oven is temperature regulated, and that allows us to encourage our separation of the sample by heating it up. If it's a volatile sample, we'll heat it up until we reach the boiling point of that sample, turns to a gas, and it starts moving through the column. I'll give you another idea of what a column looks like by actually bringing one out. So here's a column right here. Now, the columns, unlike the packed column, now this is an open tubular column. Now look how thin that is. That's pretty thin. That's almost as thin as a hair. And that is actually a column. It's a small capillary tube that's twisted around this. It's like a bicycle. It's twisted around here like dozens of times. And we can encourage very long lengths. The length of this guy, this is 30 meters long. Pretty long column. Typically, the columns will be anywhere for our open tubular capillary columns, anywhere from 15 to 100 meters. So that's a pretty long column. Long columns give us large number of theoretical plates, and they give us superior efficiency in comparison to the packed column. Their diameters are very small. They're anywhere from 150 to 300 micrometer. So they're pretty small diameter. Now, we said an advantage of the packed column is that we can put large amounts of samples. Well, that's one of the disadvantages of the capillary columns. We're limited to smaller sampling size. But the nice feature of that is it limits the amount of waste that we're going to be introducing to our environment. So that's important. Put that back. These come in boxes. Now, the types of detectors that we use for gas chromatography, these include a flame ionization detector, thermal conductivity detectors, and mass spectrometers. Now, these are different than the UV-Vis detectors that we were discussing earlier, and then we're going to discuss a little bit later. Those are used for liquid samples. Gas samples are, we don't measure an absorbance, but what we do is we usually introduce our gas sample into the column. It comes out into a carrier gas that's introduced into a flame, and the change in the flame ionization measurement that we make is going to tell us a little bit something about the amount of sample that's present. Another type of detector that's used, and we use it in instrumental lab, is going to be a mass spectrometer. So the composition of the different components within the column are usually prepared by doing some chemistry on silicone surfaces. And we modify them. Let's discuss a little bit about the modification of our silicone surfaces. I have a picture of what these silicone substances look like, and I'm going to draw it over here on the dry erase board. I'm in the laboratory, so we're working right here in the laboratory. Set that up. Okay, let's go through what these silicone surfaces look like. So hopefully everyone can see that. If not, I'll go in and make some changes a little bit later. Now, when we have a surface in a column, here's our surface. And remember earlier we discussed the silicone surfaces in thin layer chromatography. Well, once we get into more advanced methods and we got a little more sophisticated over time, we were able to conduct some chemistry on these silicone surfaces. Now, these are simply silicone, and they usually have an oxygen combined to another silicone. And we're able to do some chemistry, and we can modify these surfaces with what we call R groups. Now, the R groups that are on this silicone surface will dictate the polarity of these different surfaces. Now, we can decorate them, or we usually use the term decorating, or we can modify them. For instance, if the R group is CH3, we have a fairly non-polar stationary phase. So that's our stationary phase. If we have a non-polar stationary phase, for GC, we're only focusing on the stationary phase. A non-polar stationary phase is what we call reverse phase chromatography. This helps us to retain substances on our column that are nonpolar. Substances that are nonpolar will spend more time on our column, and we can separate substances based upon their differences in polarity. So a nonpolar substance is going to stay on the stationary phase longer, and if we look at a chromatogram, it'll be the species that comes out last. Everybody good? What if we didn't modify this at all? And we just simply kept an OH group out there. In this case, we have a polar stationary phase. Polar stationary phase. And this is what we would have in normal phase chromatography. Normal mode, I'm sorry. So this is normal mode chromatography. Normal mode, or as we sometimes say, normal phase. Now, this is called normal phase simply because this was the original type of chromatography that was conducted in the 1800s and early 1900s. They used polar surfaces. Polar surfaces retained polar substances longer on their column, and it was better for separation of polar species. So, now let's discuss the two factors that influence our separation. Again, the nature of the stationary phase is very important. So when we think of separation of a species in GC, there are two factors that we have to consider. So these are separation of components or of species. Depend upon two factors. First of all, as we just stated, interaction with the stationary phase. If we're running normal phase chromatography, more polar substance will stick to the stationary phase longer than nonpolar substances. If we're doing reverse phase chromatography, we have a nonpolar stationary phase, and nonpolar substances are going to interact with that stationary phase longer, and they'll be retained longer. But there's also another feature that we have to take into consideration, and that's the boiling point of the substances. Now, this is an important feature also, and it's one of the features that we can influence in the course of our experiment. Our column is within an oven. Now, that oven's temperature is usually going to start during the experiment a little bit lower than the boiling points of all of our substances that are in that oven. When we increase the temperature, and normally we do this in a ramp, we come up slowly. The substances with the lower boiling points are going to be able to vaporize first, and they're going to be able to come off our column first. Substances with higher boiling points, they're going to come off last. And it also, again, does depend upon how we have interactions on the stationary phase. So let's think of an experimental situation that you guys would have been dealing with in Quant Lab, the last exercise you would have done. Let's look at a little exercise here. And we're going to look at 3 species, 3 organic compounds. and we're going to answer some questions about them. So we're going to think of 3 compounds that we're putting into our GC experiment, and we're going to look at some data and make some decisions about our data. We have N-pentane. If you haven't taken organic chemistry, N-pentane is a 5-carbon chain, and each carbon is saturated with hydrogen. Oh, just lost the lights. So that's N-pentane. It's a 5-carbon chain. N-hexane. Well, I could sit here and draw the picture, but it's simply one additional carbon on that chain. So it's a 6-carbon chain. And we also have N-heptane. N-heptane has 7 carbons on its chain. We put these into our column. We inject them, put them on the column, and we get a chromatogram. And on our chromatogram, we get 3 peaks. 1, 2, 3. And we have a time. This is time. And this is detector response. Okay, I didn't give you a lot of information about the nature of the column. Okay, let's think about what these 3 compounds, are they polar or non-polar? That's the big question we want to ask. What can you tell me and think about general chemistry? When we have hydrocarbons, organic compounds that are chains of carbon, hydrogen going in a straight line, there's no substituent atoms on there, they're all carbon, all hydrogen. What can you tell me about their polarity? Take a minute, think. Give you 3 seconds. Okay, I'll tell you. These are non-polar. All of them. They're not polar. These are non-polar compounds. Three non-polar compounds. And we're putting them on a column. Guess what? Regardless of whether we put them on a polar column or a non-polar column, that's the stationary phase, they're all going to interact the same way because they're all non-polar. If we put these 3 in a non-polar column, they're all going to want to stick to the column, about the same. If we put them all on a non-polar polar column, they're all not going to want to stick on that column, and they're all going to come out pretty quick. So in this case, what's going to determine the order in which they elute, in which we see them in this chromatogram? Okay, you got 3 seconds. 1, 2, 3. It's boiling point. Boiling point is big. When all of our species that we're trying to separate have the same polarity, they're all non-polar, regardless of the column type, it's the boiling point of the substance that's going to determine which one elutes first, second, and third. The one with the lowest boiling point will come out the fastest. The one with the highest boiling point will come out last. And that's because as we increase our temperature, the one that has the lowest boiling point will be vaporized first. It goes into the gas phase first. It's going to come out of the column first. So, makes sense? Big question. Which one is related to which peak? Like, which one's sample 1, which one's 2, and which one's 3? Now, we have 3 hydrocarbons. The only thing that's different is their mass. Do you remember in Gen Chem, we talked a little bit about boiling points and mass? Okay. You can look these up also, so that's normally what people do. But if we were trying to think right then and there at that moment, which one do you think come out first? If I just asked you, or if it's an exam question and then you didn't have a data table available. So let's think about 5-carbon. 5-carbon has a lower mass than 6-carbon, which has a lower mass than 7-carbon. Remember, boiling point depends upon a sample's mass. The 5-carbon, having the lowest mass, will have the lowest boiling point. The 7-carbon heptane will have the highest boiling point. The 5-carbon having the lowest boiling point is going to come off the column first. So number 1 is going to be N-pentane. It goes into the gas phase first. Since it goes into the gas phase first, it comes off our column first. Which one do you think is going to come off second? It's going to be the N-hexane. The third one is the heaviest because it will have the highest boiling point. And number 3 will be our N-heptane. So when all things are constant, all of our samples are nonpolar, regardless of the nature of the column. What we use for separation for gases is differences in boiling points. So that's an important feature for gas phase chromatography. Next lecture, I'm going to put together another slide, another YouTube video in a minute, and it's going to deal with HPLC. So I'm going to stop this, and we'll get into HPLC just briefly in a minute or so.